Hey everybody, my name is Chris and I'm a tutor here at Chegg.com. I mostly do math and a little bit of computer science. And in this video, we're going to do an example of showing that a function is holomorphic on the entire complex plane. So here we have the function f of z equals z squared, and we want to show that it's holomorphic. So there are a few different things we could do, but what I want to do here is use the Cauchy-Riemann equations. So in general, if we have some function f of z, then we can regard that as u of x comma y plus I times v of x comma y, where x and y come from z equals x plus iy. And then the Cauchy-Riemann equations say the partial derivative of u with respect to x equals the partial derivative of v with respect to y, and the partial derivative of u with respect to y equals negative the partial of v with respect to x. Okay, so these right here are the Cauchy-Riemann equations, and what we want to do is basically show that this function satisfies these equations everywhere, and then that'll guarantee us that this function is holomorphic on the complex plane. Now there are a couple details that we're just sweeping under the rug, just in the interest of saving time and to keep things relatively simple. So the first thing that we want to do is express this function f of z as u of xy plus iv of xy. So let's go ahead and do that. So I'll set aside some space here. All right, and then let's say if z equals x plus iy, then f of z is z squared is x plus iy squared, which remember that means x plus iy times x plus iy. So we want to FOIL, and when we FOIL, we're going to get x squared and then plus 2ixy and then plus I squared y squared, which means f of z is equal to x squared minus y squared, because I squared is negative 1, so this becomes minus y squared. And then we have plus I times 2xy. Okay, so then remember we want the form u of xy plus iv of xy. So here is our u. This is our u of x comma y, and this is our v, 2xy. Okay, so let's go ahead and go to the next page, and then on that page we're going to want to show that u and v satisfy the Cauchy-Riemann equations. So remember we have u of xy equals x squared minus y squared, and v of xy equals 2xy. Is that correct? Yes, 2xy. Okay, now let's go ahead and see. So we want to make sure that the partial of u with respect to x equals the partial of v with respect to y. So let's go ahead and verify that. So the partial of u with respect to x equals just 2x, right? Because remember, if we take the partial derivative of u with respect to x, then we're going to treat y as a constant. So the derivative of this with respect to x is just 0. So we just get 2x. And now we want to verify that that equals the partial of v with respect to y. Well, here, 2xy, that's v of xy. So when we take the partial derivative of v with respect to y, we're going to treat 2x as a constant. So this is really just a constant times just the plain old variable y. So when we take the derivative with respect to y, then we're going to get 2x. So vy equals 2x. So yeah, we've just verified that u sub x, the partial derivative of u with respect to x, equals the partial of v with respect to y everywhere, because 2x is always equal to 2x. All right, but that's just one of the equations. We also have to verify this one. So let's go ahead and do that. Now we want to check that u, the partial of u with respect to y, equals negative the partial of v with respect to x. So let's go ahead and do that. So the partial of u with respect to y is actually negative 2y. Remember, treat x like a constant for this, and then we have minus y squared becomes minus 2y when we take the derivative. Now what about negative v, the partial of v with respect to y? Well, we still have a minus sign on here, with respect to x. So the partial of v with respect to x, well, we still have the minus sign on here, and the partial of v with respect to x is going to be 2y, right? Because we can rewrite this as 2y times x. X is our variable, so we treat 2y as a constant. So if we take the partial derivative with respect to x, we just get 2y. And we see that these two things equal each other everywhere. So actually what we have is u, the partial of u with respect to y, equals minus the partial of v with respect to x everywhere. All right, so what we've just seen then is that u of xy and v of xy satisfy the Cauchy-Riemann equations. And what that means is that the original function f of z equals z squared is holomorphic on all of C. And it's holomorphic everywhere because these equations are satisfied everywhere. Or sorry, what I should say is these two equations here are satisfied everywhere. Therefore, this function f of z equals z squared is holomorphic on all of C, the complex plane. Okay, so this has been an example of showing that a function is holomorphic, and I hope you found it helpful, and thank you for watching.